Hello everyone. Welcome to today's ASAP seminar. Today we are very happy to have Lifan Yuan to talking about from XPX to NGX to FGX. LLMs can learn new skills in RL by composing the new ones. Lifan Yuan is a second-year PhD student at UIUC, advised by Professor Peng Haopeng. His research pursues scalable AI systems that can automate AI research through self-evolution and accelerate sets. He works on scalable data synthesis, evaluation, and training of large language models, with a focus on reinforcement learning and reasoning. He has worked at the Gemini team at Google DeepMind as a student researcher. Let's welcome Lifan to talk about this topic.
No. Okay, hi. Thanks to you for the introduction and hosting me. Well, let me share my screen first. Cool. Hi, I'm Lifan, a second-year PhD student from UIUC. Today, I'm honored to present my recent work on RL compositionality, that is, how LLMs learn new skills in RL by composing old ones, and share my thoughts on RL for LLMs. This talk consists of three parts. First, we talk about motivation on why do we care about if LLMs learn skills in IR. And then we introduce the experimental approach to answer this question in a clean way. And finally, we will go through the findings. To begin with, let's take a look at the ongoing debate in the open community. Does RL teach LLMs genuinely new skills, or does it merely activate existing ones? This was not even an issue in traditional RL literature, evidenced by many applications. One of the famous examples is AlphaZero. Look at this figure from AlphaZero paper. The model performance starts from zero ELO score, but ends up surpassing human experts. However, recent work on LLM reasoning show that the so-called emergent aha moment is not entirely new to the model. The long COT reasoning can be traced back to certain existing cognitive behaviors, for example, backtracking or verification, and RL simply amplifies these patterns during training. Specifically, Quinn models already present these behaviors in the base model. Thus, directly IL from the Quinn base model leads to a reasoning model that performs self-reflection. In contrast, there is no such behaviors shown in Llama. So RL fails to teach self-reflection until a SFT stage is performed before RL to prime those cognitive behaviors. There are some other work showing similar spirits, thus posing a doubt on whether I'll truly introduce new skills to the model. But why is there such discrepancy between traditional R literature and findings in LLMs? One essential difference is the action space. In traditional R, the valid action space is much more limited. So it's possible for the model to sample high-quality rollouts from scratch. And in contrast, the action space for language models consists of tens of thousands of tokens. Thus, it is necessary to pre-train the model to get a fairly good prior. On one hand, the prior helps the model to generate reasonable trajectories, but on the other hand, it may also constrain the search space, limiting the exploration of the model during our training. Why do we care about the debate at all? It's because the answer to this debate impacts important decisions in the life cycle of LLMs, especially informing the high-risk trade-off in resource allocation between pre-training and post-training. Specifically, if RL only activates existing patterns in the base model, then it means base model itself is more important than those RL algorithm tweaks. Therefore, we should prioritize better pre-training techniques, data, or more compute to build better base model for RL. However, if RL teaches models with new skills, then we can improve models by refining the RL process to unlock novel skills. For example, putting more efforts on designing better RL algorithms or data recipes. Answering the question motivates three concrete research questions. First, does RL teach new skills to LLMs? If so, how to incentivize it? And third, are these learner skills generalizable? As a preview, we designed a controlled experiment on synthetic tasks and show that first, I'll indeed teach new skills by the means of composing old skills. And second, incentivizing the learning requires the IL training task to include explicit incentive for composition. And finally, we show that these compositional skills generalize to held-out evaluation, multiple questions, and even a different task. Our motivation comes from how humans acquire cognitive skills. It is well established that humans acquire cognitive skills in three steps: learning basic knowledge, composing sequences of actions into a single complex one, and finally, internalizing the new one. Here, I'd like to acknowledge my friend Yuan from UW, as I got this intuition from our conversation on how he was so good at coding competitions, where he basically described a similar process. We conjecture that the learning process of LLM through RL may be similar to humans. Therefore, we propose the following hypothesis, which we call our compositionality hypothesis. That is, once a model has acquired the necessary atomic, non-decomposable skills for a task through NTP training, RL with proper incentivization can teach the model to learn new skills by composing atomic skills into complex capabilities. So next, we will introduce our methodology to perform a clean and controlled experiment to test this hypothesis. We will show that SFT on compositional skills only teaches solid atomic skills, but not generalizable compositional skills. So does further RL on atomic skills only. However, RL on a set of simple compositional data for incentivization unlocks novel skills. The meta skill of composition generalizes to held-out evaluation, harder problems, and other irrelevant tasks. So let's move on. Let's move on to part two. It is very important to reduce or eliminate spurious correlation between the base model and the evaluation task, and to clearly distinguish atomic skills from compositional one. Therefore, we need to carefully design a testbed satisfies three requirements. First, the task should be fully decontaminated and the data does not appear in LLMs pre-training. Second, atomic skills should be well defined. And finally, the task difficulty can be controlled for a comprehensive analysis. Inspired by physics of LLM series of work, we then proposed a synthetic task, namely string transformation prediction. Specifically, given a string input x and deterministic string transformation fng, the task requires an LN to predict expected output y from f of g of x. Each transformation, such as fng alone, is an atomic task, and the nesting of functions is considered a compositional task. Now we illustrate how this task satisfies our requirements. First, each string transformation is a unique function assigned with a meaningless identifier, such as func16, to prevent any inference from function names. During IL, function definitions are hidden. The task will then be unsolvable without going through the atomic skills acquisition training. This setup enables us to investigate the research questions controlling for confounders. And as we said, we define atomic skills as single, non-decomposable transformations, and compositional skills as their nested combinations. For example, given the input string x, func 16 of X represents an atomic scale, while func 16 of X requires a compositional reasoning. As each skill is instantiated as a Python function, we control the difficulty of composition through the depth of nesting. The model must perform deductive reasoning to predict the output string after a given transformation. For example, as shown in this figure, the func system of X is a level 1 difficult question, and the func system of func 15 of X is a level 2 problem. Here, the difficulty level is determined by the number of atomic functions composed. Okay, now we move on to the training and evaluation based on this framework. As we said, our atomic task is unsolvable without an explicit atomic skill training. Therefore, in stage 1, we perform rejection fine-tuning, shortened as RFT, to train function definitions into the model. Given full definition and string input, the model samples rollouts and train on those correct ones only. For example, in this figure, it shows a prompt for a stage 1 training. The function body of the function is fully provided, and the model is tasked to predict outputs given a random input string. We iterate the training process for 2 epochs to make sure that the model has a decent understanding on atomic skills. Next, we investigate how we can enable the learning of generalizable compositional skills. The training algorithm can be either IFT or RL. However, the data given varies. Unlike stage 1 training, where the model is only fed with level 1 atomic task, now the model can receive problems of any difficulty level. But for all runs, the function definition is hidden. For example, in this figure, the function definition of func system is not shown anymore. This prevents the model from solving the problem accidentally by simply relying on memorization. Therefore, the model requires performing actual compositional reasoning to obtain a correct rollout. And that's how we explicitly incentivize composition. The major evaluation setup consists of held-out evaluation and easy-to-hard generalization. Held-out evaluation means that the atomic string functions appear in stage 2 training is totally different from the ones in test. More specifically, we have 25 atomic skills in total, all used in stage 1, so that the model can memorize all function definition for later use. However, only 13 of them, that is the function 1 to function 13, are shown in stage 2 training, and the other 12, function 14 to function 25, are shown in test set. For easy-to-hard generalization, we perform stage 1 training on level 1 problems only, and stage 2 on level 1 or level 2. However, the evaluation is conducted on problems from level 1 to level 6. Any questions on the setup? Okay, then let's move on. In the first experiment, we examine if LLMs acquire new compositional skills. We adopt the vanilla stage 1 setup, but consider 3 different data setups in stage 2. Are on level 1 problems only, on level 2 problems only, or on both level 1 and level 2 problems. Note that training on level 1 problems do not explicitly incentivize composition. Results of R on level 1 problems, that is on atomic data, is shown in the dark blue line in this figure. Different suffix represent different difficulty levels of test problems. Training on level 1 alone leads to high accuracy on level 1, peaking at around 90%, but failed to generalize. Its accuracy on level 2 remains below 25%, and on level 3 through 6, it is consistently near zero. So, in short, the takeaway is that RL on atomic data leads to very high accuracy on atomic tasks, but it is insufficient for learning effective composition. In contrast, incorporating compositional tasks into our training yields transformative results. Both the RL on level 2 and RL on level 1 and 2 models demonstrate strong performance to generalize to performance with nesting depths exceeding layer training data, as shown in the yellow and red lines respectively. On level 3 and 4, their accuracy improves significantly rather than presenting a flat pattern as in the RL level 1 model. And this trend continues even on level 5, indicating both models have learned a generalizable principle of compositional reasoning rather than merely memorizing solutions. This validates our hypothesis that RL can teach genuinely new skills, but only when the training objective explicitly incentivizes their use. Training on compositional data is an easy way to provide the incentive. The previous experiments show RL on atomic data does not work, while with a proper incentivization teaches new compositional skills. So now we know that compositional data is important. However, is RL also necessary here? Can a supervised method such as IFT achieve the same results as RL when given the exact same compositional data? Therefore, we next compare RL with iterative IFT using the same level 2 training prompts. The IFT model's accuracy is significantly worse than RL across all compositional levels and has only marginal improvements over the first iteration. In this figure, the red dot denotes the performance of RL on level 2 problems, while the 6 bars in each fig indicate the 6 iterations of IFT on level 2 problems. The IFT model's accuracy is significantly worse than RL across all difficulty levels and has only marginal improvements over the first iteration and even degrades. This indicates that IFT failed to generalize to held-out compositional problems of the same difficulty as its training data, let alone higher difficulties. Therefore, we conclude that IFT, even with compositional data, is suboptimal for learning compositional skills, while RL is an important factor in learning generalizable compositional skills besides the data. While our experiments demonstrate that RL can teach generalizable skills within a task, collecting compositional RL data for every new domain is impractical. We therefore test the transferability of the learned compositional skill. Specifically, we hypothesize that the compositional skills are transferable from task A to task B if the model has learned atomic skills for task B and the compositional skill has been learned through RL on task A. To validate this hypothesis, we still use the string transformation prediction as the source task for RL and expect it to transfer to the target task, countdown. As shown in this prompt, countdown is a synthetic math problem requiring the model to create an equation using a given set of integers to reach the target number. The size of given set the size of given set indicates the difficulty level of countdown. For example, in this case, it provides four numbers, so it's a level 4 problem. The atomic task for countdown is level 2 problem rather than level 1. The training setup here is a bit complex, but in short, we first created an ideal setup that satisfies the requirement in our hypothesis, that is the first one in this table, the multi-base with R on level 1 and 2. It is trained with atomic skills of both string task and countdown, and that's why we call it a multi-base, namely the base model that is SFT'd on multiple tasks. The model then goes through RL on compositional string problems. Next, we apply atomic skills of countdown and compositional problem of string task respectively. The first row, a single base, applies the atomic skills in target task. The second and third row apply the compositional RL in such task, either removing RL at all or only using atomic problems. For the bar chart, we can see that the string base with level RL level 1 and 2 model fails completely. The multi-base model without RL on level 2 data achieves reasonable accuracy of around like 20% at level 3, but still struggles at higher levels. RL on atomic data shows marginal improvements. Our ideal setup, the multi-base with RL on level 1 and 2 achieves strong performance at level 3. And this advantage persists at higher complexities, where other models largely fail and achieve like near zero accuracy. The results show that the compositional skills learned through RL are transferable from a different task where the model has possessed the atomic skills. Our findings on task transferability may help explain some recent findings on generalizable improvements from RL. For example, Logic RL observes a performance boost on unrelated math problems after training on logic puzzles, and the Guru models show that domains with better exposure in pre-training data benefit more from cross-domain generalization. From our perspective, they may both be accounted for the fact that modern LLMs have already gained necessary atomic skills during large-scale pre-training, especially for math, code, and science. Therefore, incentivizing compositional skills by RL from another task helps combine task-specific skills in those tasks more effectively. And in contrast, domains that appear less frequently in pre-training data may not have learned sufficient atomic skills, and thus improving compositional skills may not necessarily lead to better downstream performance. Our findings strongly suggest that RL can teach compositional skills that are novel to the base model. However, recent work claims that R merely re-ranks the model responses, distilling parsec K performance of the base model into parsec 1. Next, we revisit the claim by performing analysis at varying difficulty levels. We compare the parsec 1000 performance at each difficulty level of our test set. Both RL level 1 and RL level 1 and 2 models are trained from RFT-based model using RL in stage 2. And the RL level 1 model, which is not incentivized properly to learn composition, exhibits similar trend to the RFT-based model across all levels. And on easier problems, that is level 1 and 2 in this case, where the RFT-based model already shows solving potential, evidenced by the high parsec K. The performance gaps between RL level 1 and 2 and the RFT model shrinks as K increases, aligning with the trend observed in prior work. However, A completely different trend is observed on more challenging compositional problems, that is the level 3 to level 8. The IR level 1 and 2 models' performance substantially outperforms the RFD base, with an increasing gap as K grows. And this divergence is clear evidence of new skill acquisition. Then why do we get these different results as previous work? We pose two conjunctures. First, a previous work evaluates and trains on tasks where the base model already achieved high parsec K. Therefore, we claim that IL may have little incentive to learn a new skill on these tasks. Second, the aggregate parsec K metrics on mixed difficulty benchmarks can mask an improvement in a specific skill like composition if other required skills remain a bottleneck. In contrast, our framework enables decontaminated evaluation and fine-grained analysis on challenging problems. Therefore, ensuring the base model performs poorly on test set and providing analysis on various difficulties. So far, we have gone through the experiments, so let's have a findings review. First, we have confirmed that LLMs learn new skills by composing O1s. For that learning to happen, both RL and incentivization to composition are required. Second, the learned skills generalizes to held-out evaluation, more difficult problems, and even a different task. And finally, the learning of new skills can also be reflected in parsec K when evaluation is done rigorously. That is, evaluating on problems where the base model does not already achieve a very high parsec K. Closing the talk, I'd like to share my personal thoughts inspired by this work. First, I want to highlight the critical role of RL, as everyone knows, but particularly for its generalizability. We already know that RL use very decent performance for LLM post-training, and this is what everyone is doing and sounds cliche. But now, hopefully, we have a better understanding on its easy to hard generalization. Therefore, is it possible to maybe iteratively internalize the latest composition as new atomic skills? Just like what we described in human acquiring cognitive skills, so that the model can eventually solve extremely complex problems directly without like a complex reasoning. And second, we suggest building base models with various atomic skills. In our countdown experiments, we show that atomic skills in target task enables cross-task transfer to happen. Therefore, the question is, by equipping base models with various atomic skills, can we leverage the cross-task transferability of compositional IR to reduce data collection efforts on tasks where gathering IR data is costly or very difficult? And finally, we suggest a closer coordination between pre-training and post-training from a skill acquisition perspective. That is, pre-training should optimize not only for base model performance, but for post-training potential and efficiency. For example, can we propose some metrics for the base model to indicate post-training performance from this perspective? Perplexity was a good metric for a base model, but for better coordination of the pre-training and post-training, we may need something new. And can we flexibly reallocate data collection efforts between pre-training and post-training based on where data is easier to obtain? For example, can we move the difficult to collect post-training data upstream to pre-training? And vice versa, can we put like those difficult to collect pre-training data to delegate it to post-training? So we can have it like a better final model performance, not just like a best performance in every single stage. Okay, That's all for my presentation. Thanks for listening and look forward to questions and feedback. So,
Hi, Lifan. Thanks for your work. And recently, I'm trying to reproduce your work. And I see that you now you don't open source your training data sets. So I wonder in the future whether you will uh, open source your data.
I think we have open source to the data, but I will double check. If it's not open source, yeah, I think we will open it like maybe today. Yeah, sorry.
I, don't- I in your GitHub code base, I don't see the data link.
Okay, yeah, I remember we prepared for the open source, so yeah, let me double check. Sorry for that.
Oh, thank you, thank you. I wait for your data.
Yeah.
And I also wonder how much time for you to uh, generate data and model response at each stage, and then how is the training time for each stage? For example, the stage one is RFT, the stage two is GR depot. Yes.
Well, I think your question is like the first is like the data is data generate how the data generation before the training like or like are you or do you mean like the rollout sampling stage?
Yes, because I try to run your code on AMD GPU, and it I I guess maybe will take me about 11 days.
11 days for IL training?
No. Generate model routes.
No, I don't think it should be like a that costly. I think
Oh.
the data the final response length is like similar to what we observed in math training. So I will say it should be very similar to how you train a model on math. So basically,
Uh, I don't mean training. I mean preparing for the training data.
the preparing for the RFT data.
Yes.
I think like we just cost maybe 10 around 10 hours on one node of A100.
So what's your computation resources?
I think we mostly just rely on every experiment is finished on single node of A100.
A100. Okay.
Yeah.
Okay. How about your training time for the uh RFT and depot?
I think RFT is like a very lightweight stage. We we only go through maybe 20,000 examples. So I think if you just like around one or two epochs, it should cost like less than 1 day.
Okay. How about the RL training?
Our training should be like several days, but I don't think it will be too heavy. Like if you can easily train your model on math, then it will I think it will just be similar. Yeah.
How many days?
Uh, to be honest, I don't remember the concrete numbers, but I think it's like 2 or 3 for us to complete each set of experiments.
2 or 3 days.
Yeah.
Oh, okay. So,
And I think
uh,
like the the main bottleneck for completing for completing its experiment is like to sample the Pascal test set, not for the training. Yeah.
Okay. Thank you. I think maybe the speed for AMD is slower than A100. So wait for your open data sets. Thank you.
Feel free to send me a follow-up email if you have any other trouble.
Okay, I will. Thank you.
Yeah, maybe I can also ask some questions. First, I was wondering that have you think about uh, whether the post method can, for example, because you mentioned that it can generalize from the simple task to conversation ones, do you try to maybe to more complex compilation ones, such as level 3, level 4, and maybe something like level 100, something like this? Is this possible for it to using just a pure RL on the just a unit task or atomic task can continue generalize, or we also need some fine tuning, standard fine tuning, or some composition task when its level comes too large.
Yeah, so yeah, I think the question is like what you're mentioning on Twitter, right? Like
Yeah, yeah,
can
yeah.
yeah, I think it's basically this question. Actually, we tried some primary experiments. Like, for example, in current experiments, we only train on like level 1 atomic scales and generalize to level 3 and 4, and then we tried to maybe IFT the level 3 and 4 back to the base model and continue training. But currently, we made a bottleneck that the trajectory for level 3 and 4 is already very long. So actually, we will have some long contest issue for training. Say we will, yeah, the response length will grow continuously. So yeah, I
I
think
see.
if we can manage this, we can continue that exploration. But for now, we don't have very concrete conclusions.
Yeah, yeah, because I think that I also observed that some recently post-training work, they also try to iteratively do supervised fine-tuning in the RL, and maybe that just means that if the model can itself generalize to composition task, maybe it can just roll out its own trace and then do supervised fine-tuning on this trace and then further generalize to more difficult tasks. Yeah.
Yeah, and maybe I can share another ongoing work is that we are not going to like a RFT, like distill the generalize the level 3 or 4 trajectory battle model, but just like we are continuously train the the model on a single task. For example, still say the countdown, and it would directly train it on level 2, and you can kind of like it gradually increase its accuracy, improve its accuracy on level 2. And then if it consistently solve the level 2 problems, we can kind of like feed the level 3 problems to the model. Like it's just like a curriculum learning. We can continuously feed more difficult problems step by step. And we have observed some the model gradually solved more and more difficult problems. Yeah.
I
But
see.
it's like pure RL, not just like an IFT stage.
I see, I see. Yeah, it just means that pure RL can also scale to difficult tasks. Yeah.
Yeah.
Yeah, so another maybe related question is about because you mentioned countdown, yeah, but I think that one challenge is that in real world tasks we are hard to know, for example, the level of the maybe the difficulty of the tasks. Yeah, how can we, for example, to apply such method to real world RL tuning? Yeah.
Yeah, that's a very good question. I think a question is like how we identify those atomic scales
Yeah,
in
yeah, that's
yeah.
right.
Okay. I don't think like in this experiment we tried to, for example, made a clean conclusion to so we just like have a atomic scales. But actually, I think just like if we can internalize those complex composition as the new atomic one, I think it can also be composed, just like how you nesting functions, right? So basically, I just say I don't think it's necessary to be level 1, specifically level 1 for each task. Maybe it's just have a great coverage of all these basic skills. For example, for countdown is level 2 because you need two numbers to complete a number equations. But For example, for a real world task, maybe there are higher level, higher difficulty level of data, but it already covers it consists of many atomic scales. We are not able to identify those atomic scales, but those compositional data already cover it. So I think hopefully it will work. So that's what I think it is similar to this question. That is like, yeah, your first question. Can we like iteratively internalize the latest composition as atomic scales? And if it holds, then it means that the atomic scales itself may not necessarily be like the non-decomposable ones, but can be like already a composed one. Yeah.
Yeah. I think that I remember that there is a one previous work that although I think they mainly focus on the pre-training or maybe standard fine-tuning, but they mentioned that if you, for example, you have all the atomic task and for the maybe just if you consider the composition of two atomic tasks, you do not need to cover all compositions. You can maybe just cover maybe some majority of them, yeah, or just a part of them, and then you can scale to all of them, yeah.
Good morning and welcome
Yeah.
to San Francisco.
Sorry, you mean like we don't have to cover all the atomic scales in pre-training or yeah, I don't think like I fully got a question, sorry.
Maybe it's not a question. Sorry, it's just I'm in the airport. Yeah, I just want to say that one previous book they say that during pre-training, for example, you know that you have 100 just atomic task. You do not need to have training data about 90 100 the 90 100 composition tasks this to train your model. You only, for example, you only have 100 of them. Just means that you do not need to cover all the composition. Yeah.
Yeah,
And scale. Yeah.
I think like if you only have a part of those atomic scales, it's definitely possible to train the models. Uh, it's definitely because like especially if it's a long tail distribution, maybe those 100 is already good enough, and you can already use it to compose something. And according to like those generalizability and transferability, I believe it can somehow generalize. But I think the question is, can we expect RL to automatically learn those learn those atomic skills by itself? Yeah, I think it's a very interesting question, but it should be a different it should be a different perspective. Say, we are investigating if we can if we already have atomic skills, can RL learn some more complex ones? And your question is more like if you have a set of atomic skills, can it just like kind of generalize to automatically learn another half of atomic questions?
Yeah, because I think both should be important because that
Yeah.
because that you can imagine that if you have so many atomic tasks, it should be impossible for you to for each conversation and you create a question, a query, and to do RL on it. It will be very expensive, yeah, because it will scale exponentially with the increased level of the conversation, yeah.
Yeah. I agree. And I think that's partly what I said, like a better maybe data re reallocation between pre-training and post-training. For example, some data may just be very expensive to collect in pre-training data. So you kind of like want to just push it in the post-training data, you directly train for it. Yeah. And sometimes if the post-training data is more difficult to collect, you just want to like prepare a set of RFD data set and training. So it will be much
Yeah.
easier. Yeah.
Yeah, and I was wondering regarding you mentioned when the level increases, the long context becomes a problem. You want to say about just means that the model do not have a good performance or long context, or it is just very expensive during training.
I think both. Like if it becomes really long and it will be truncated. So the model like you the model the model hasn't like reached the answer and the rollout is truncated. So you've barely like a sample a correct rollout. So this is yeah, I think this is a common issue in long COD training, I think.
I see. I think that I guess that yeah, just I think that it is a common problem that of the existing autoregressive models here, because that it can only always increase its generation. Just I imagine that even sometimes if you can, for example, like recently that people trying to doing some compression that on the memory, that if you can compress the context and maybe ignore maybe some past just use this information, maybe it can scale much better to longer
Yeah,
context, more conversations. Yeah.
yeah. And we're trying this. We are exactly trying this kind of techniques to uh try to see like how it goes.
Yeah, because I agree that with the increase of the conversation numbers, that even in real world task, I guess the context length should be increased. And in that setting, that the behavior of the transformer changes, and it will increase maybe the difficulty, and maybe it's hard to train. Yeah. But if we make it something like maybe compression, just means, for example, we ignore the past atomic ones, we only focus on the current ones. Maybe it can scale. Yeah, this is just maybe assumption. Yeah.
Yeah, I agree. So maybe like when we iteratively internalize those latest composition, we should also like consider how to compress it, not just like directly distill it. Yeah. Otherwise, I think the long context will always be an issue.
Yeah, because I think that on synthetic task, it should be not very hard to do this compression. Yeah, because that you know what each atomic task is. But in real world, that we do not know what other atomic task. Yeah, so it will be more challenging. Yeah.
Yeah, so that's part of my complaint on like long COT reasoning. I feel like
Yeah.
tokens are redundant, so actually you just need some words to maybe log some intermediate results, and that's good enough for you to continue the reasoning stuff. But with the long COT, you must put all maybe misleading reasoning trajectories in your context. So and it's not just a problem of efficiency, but also I think it's kind of a performance issue.
Yeah. I think so. Yeah. I think it's very interesting. Yeah. Just means that we have more strong evidence for some new architecture. Yeah.
Yeah, I think like I'm not against those long chain of thought, but maybe we just need some maybe context controller or something, not put everything, not just putting everything on the context. It would be unnecessarily long.
Yeah. I have a question just to make it more concrete. Could you please name several atomic and compositional skills in this string manipulation domain?
Uh,
And and then I'll have a follow-up question. How many skills do you think are necessary, atomic and compositional, to completely master this domain?
okay, sorry. So your question is like, how many atomic skills are necessary to finish the composition?
Yeah, just to make, I mean, I have a kind of fuzzy understanding of this issue. If you could please explain, give a couple of examples of atomic skills and compositional skills, and then maybe we could think about how many skills do you need to have a complete skill set?
Uh, okay. You mean like how many atomic skills we need for a
Yeah,
com
just let's begin. Like, what is an example of an atomic skill in this domain?
yeah, you can just look at this example. It's basically a string function, a string transformation. So
Like,
yeah, I
mhm.
think it's like a created from it's created. So we don't have a say complete set of composition because the composition is uh, entirely determined by how we created those atomic skills. And we created like 25 different atomic skills.
You mean 25 different functions?
Yeah. Say this is the existing functions, and we have 25.
And like, okay, so each function basically is a kind of a different algorithm.
Yeah.
Writing on strings. So string input is like signature is input is a string and output is another string, right?
Yeah. This function input a string and output a string. This is our what we call a string transformation prediction task.
Okay, so and any change in this function, you would name it a new atomic skill.
Sorry, train of thought?
So if you like do some kind of mutation of this function, any change, like add another concatenation inside, that it would constitute a new atomic skill.
Yeah, like we will not we will like we carefully design this string function so that the functionality that do not overlap. So basically, like I don't think there are any similarity between each atomic skills. That's why like in our setup, at least in our setup, we will try to control this experiment. So the compositional the full set of composition will be determined by like how many atomic skills we defined. So it's not like how many atomic skills we need to complete this composition set. So I think it's a reverse view. Yeah.
So basically, you have a set of input-output traces, and you say that your set of skills completely could explain this set of input-output examples, right?
Mm-hmm.
Okay, and then what would be a compositional skill?
A compositional skill is yeah, just like this. It's a nesting. It's a nesting of two functions.
Okay, I see. So like, what's the difference between them? I mean, there is no, I mean, it's not a abstract definition, right? It's not a theoretical definition. So basically, you are saying that, okay, so if so basically the reinforcement learning could discover compositions, but can't discover this atomic skills. That's the main thesis, right?
Okay, sorry, you mean like by this approach, can it discover atomic skills?
Yeah, you say reinforcement learning training, you need to have
Yeah,
atomic skills where I mean you have a data set which generated by atomic skills, right? And
yeah. Say like atomic skills is like we define those single functions, and then in the stage one training we provide all these function definitions to the model and ask it to sample correct rollouts so that it can like use IFT to memorize all these function definitions. And then during RL, you can see from this example, the function definition is hidden. Say, you cannot just infer what does a function system mean. You can just require memory to do this so that we can apply the base model to apply the contamination in the base model. Yeah. So yeah, this is how we hide this function definition. So
okay.
mm, yeah, so I actually did not quite get our question. Maybe you mean
Yeah, and then if you move on to compositional skills, so here is like only one example of a compositional skill. Could you have like a different variant of compositional skill?
okay. Yeah, I only have another case like a countdown here. Okay, say in countdown is like given a set of integers, and you ask the model to create an equation, for example, equals to 65 here. But the basic atomic skill is like a two number. For example, 1 plus 1 and 1 minus 1 or 1 multiply 1. Yeah. So basically, the atomic skills is level 2. You can complete a numeric operation. But for level 4, it's just like you can use the same operation, but with more complex structures, and you can always divide these problems maybe into first you consider one number and like three others, and yeah, you can just do it recursively. So this is also kind of like compose those very basic numeric operations.
So what are the compositional skills like variable substitution, then you know kind of what is it called? I forgot what's name, you know, in Prolog when you match substring expressions. This also would be a compositional skill, right?
Mm, yeah, sorry, you mean like how to automatically learn the
No,
substitute?
I just wonder if there is a complete set of compositional skills, maybe it makes sense to define them and a kind of train a model to learn all the skills that are needed, like minimal set of, which would make a set of skills kind of, so to say, Turing complete or something like that.
Oh, yeah. Like in our experience, we did not explore like to apply the atomic skills in IFT stage because in our setup, as you see, um, the function definition is hidden in our stage. So you must have some way to train this function into the model. Otherwise, like say, it's impossible for it to complete this inference. But for our stage, we do have a held out setup. That is, we use 13 atomic functions in training, and then the test set is completely like another 12 set of functions. So basically, I think besides those, I think there are maybe two kinds of compositional skills. The first is like this nested function itself. This is a kind of a complex string transformation. This is a new compositional skill. And another compositional skill is kind of a meta skill to compose. The skill to compose. That is the ability to learn. So basically, I think our held out experiments also show that even if it's only R out on a set of the composition on a set of atomic skills, it generalizes to, for example, if it's trained to like compose function 2 and function 16, and maybe it already saw like function 1 and function 3 in RT, but not in RL stage. uh, our experiment show that it can still uh, try to complete those like if you given a function 1 of function 3 of x, it can still complete the task. So it not just learned how to say this specific function, but also like the skill to compose. So we don't need a very comprehensive set of atomic skills to show in RL stage.
Okay. And what about generalization? Is it's not a skill, right? I mean, if, for example, if you have an example with scalars and then you generalize it to a function of vectors, is it a skill?
You mean like if we train yeah, just look at this figure, you mean if we train on this level 2 and generalize level 3, right?
Yeah, I don't quite no. Like, for example, you have a function defined on a scalar, and then you want like change the variable type, generalize it to a vector. Is it a skill like generalization?
Mm,
Learn it? Could you learn to generalize? So it's like entirely orthogonal to your research.
well, sorry, I tried to understand the question.
Generalization is coming from concrete examples to kind of more general setup that covers those examples.
Mm-hmm. Well, I think I think you're trying to argue, for example, what's learned as a skill and what's learned as a general what's generalized, not just like a learner skill.
Yeah, you are talking about compositions
Yeah,
only.
yeah.
What about generalization, like
Gen
in a narrow sense?
Generalization, I think we have two set of like generalization experiments, say like easy to hard and held out. Like held out is what I just described. If we train on a half of atomic skills, and then we learn the skill to compose, and this skill to compose does not only apply to this training data set, but also apply to the test set. So this is a generalization of the meta skill learned. And for easy to hard, it's like we train on level 1 or level 2. That is, only one or two functions will show up in RL, but we test on, for example, to compose 6 functions. This is entirely new to the model. So the model must to generalize what it learned to compose the meta skill to these like level 6 problems.
Okay. Okay, I'll have to read your paper. It sounds very interesting. Thank you very much. Very interesting work. Thank you.
Yeah, thank you for your questions.
Is there more questions? I guess that if there's no more questions, that we can end here today. Yeah. Thank you very much for the talk. Yeah, I think that it is very important from my point of view. Yeah, because that we need to understand what RL brings to us and how we can use it. Yeah.
Yeah. I personally agree. Like especially in the open community, like in the past few months, many claims that maybe I was just like try to activate something. So I think it's very important to have a maybe not the right view, but better understanding of what I can actually achieve, so that you can really design the most suitable pre-training and post-training together to just like unlock the potential of language models.
Yeah. And I think it also reflects why it is very important for us to select the order of the queries that during RL training. Yeah, we want to make it to be a curriculum that's iterative improvement. Yeah.
Yeah. I agree.
Yeah, I think that we can end today. Yeah, thank you very much. Yeah, let me stop recording now. Yeah.